Welcome to the Deep Dive. Today we're diving into how AI is learning to truly see and understand the world around it. Moving beyond just identifying objects
Right.
to grasping complex, even unspoken instructions,
Yeah.
sometimes across multiple images. We're talking about universal visual grounding.
Exactly.
Yeah.
Think about those times where you want a computer to just get what you mean visually without spelling it all out, like
Yeah.
asking which of these shelves could actually hold all the things in that box. That takes understanding relationships, capabilities across different scenes.
Right.
The source paper we looked at uses a great example. Which furniture in image 2 can deal with the objects in image 1? It really highlights the challenge.
Okay. It's definitely not just spotting a chair or a lamp anymore. It's about the functional connection, maybe between things in totally different pictures.
Mm-hmm.
And to tackle this, we're looking at a new model, UniVG-R1. Our main source is the research paper detailing this model, plus some images they used.
So our goal today really is to unpack how this UniVG-R1 thing works, how it's trying to boost its reasoning for visual grounding, and, why it's a pretty big step forward.
Okay, let's start there then. Before UniVG-R1, what were the main roadblocks? What made these older methods stumble on these kinds of complex tasks?
Well, like the paper points out, traditional methods were mostly geared towards simpler things. Find the red car in this picture.
Single image stuff.
Yeah, exactly. They weren't really built for implicit requests or connecting info across multiple images, that example again. Which furniture in image 2 can handle the stuff in image 1? A standard system would likely just freeze up.
It can't make that leap.
Right. It needs to reason about purpose, compatibility, stuff shown separately. It's like imagine using a basic image search to figure out if your suitcase fits in a specific car trunk. It's that kind of implied understanding that was missing.
So they could maybe identify the suitcase, identify the trunk, but couldn't connect the dots in a practical way.
Precisely. They lacked that diaper reasoning you need when things get layered with text and visuals interacting. Finding something directly,
Yeah.
understanding intent or connections between images, much harder.
Okay, so that sets the stage for UniVG-R1. It's described as a reasoning-guided multimodal large language model, MLLM. What does reasoning-guided really mean here?
It means it's specifically built, engineered even, to get better at reasoning for these universal visual grounding tasks. It's not just processing text and images side by side. It's trying to actively understand the relationships, the implications, within and between them, using a structured thought process. That reasoning guided bit is really the core idea.
And how does it learn to reason better? The paper highlights a couple of key innovations. Let's talk about the reasoning-guided training data first. Sounds important.
It's absolutely foundational. One of UniVG-R1's big strengths is this meticulously created chain-of-thought grounding dataset. GO, for short.
Chain of...
Yeah. So it's not just questions and answers like coordinates on an image. It actually includes detailed reasoning chains. Think of them like showing your work in math. Step-by-step thought processes explaining how to get to the right visual answer.
Okay.
They put together about 90,000 of these examples, covering all sorts of different grounding challenges.
Whoa, 90,000. That sounds intensive. How did they generate all that detailed reasoning?
It was a pretty clever setup, actually. They used a powerful existing AI model, Qwen VL-Max it's called, which gets both text and images.
Okay.
They had it generate potential reasoning steps for different questions, like several possible ways to think through the problem. Then that same model would actually evaluate its own suggestions and pick the one it thought was best. But crucially, they didn't just trust the AI blindly.
Yeah.
They had humans review a bunch of it too. Experts checked if the reasoning actually made sense and led to the right spot in the image. And the paper mentions this really high acceptance rate, like 99.87%.
Wow.
Which suggests the automated generation was pretty darn good to begin with.
So it's not just showing the model the right bounding box, it's showing it how to logically arrive at that box.
Yeah.
Like giving it worked examples.
Exactly. That's where reasoning guided really clicks. By training on this data, the model starts to internalize what logical steps look like for different kinds of visual problems. It learns to break down complex instructions, complex scenes into manageable chunks.
Okay, that makes a lot of sense. So you've got this great data showing the model how to think. What's next? The paper talks about a two-stage training process.
Right. This is the second big piece. The training is split into two main phases.
Okay.
First is cold start supervised fine-tuning, or code SFT. Basically, they take a pretty capable base model, Qwen2VL7B in this case, that already understands language and visuals pretty well,
Uh-huh.
and they train it specifically on that detailed code data set we just discussed. The goal here is just to get the model to learn to follow those structured reasoning steps.
Well, laying the foundation.
Exactly, giving it a strong initial grasp of how to approach these problems logically.
Makes sense. Get the basics of reasoned thinking down first. What about stage 2? That involves reinforcement learning and something called GRPO. It sounds a bit more involved.
It is a bit more sophisticated, yeah. Stage 2 uses reinforcement learning, or RL, specifically an algorithm they call Group Relative Policy Optimization, GRPO.
GRPO. Okay.
Now, often with RL, you have another AI, a critic, judging the main AI's performance.
Right.
What's cool about GRPO here is that it skips the critic. Instead, it uses really clear, measurable rules to figure out if the model's answer is good and well-reasoned.
Rules like what?
For visual grounding, it's things like accuracy, how well the predicted box overlaps with the real answer. That's measured by IOU, intersection over union. And also, did the output follow the right format? Did it include the thinking steps properly?
So it's getting direct feedback on, did you find the right thing and did you show your work correctly?
Precisely. And the group relative part means the model generates a few possible answers for each question. Okay? Then GRPO evaluates these answers based on those rules and figures out which ones in that group are better than the others. It encourages the model not just to get the right answer, but to use better reasoning pathways to get there.
That's a clever way to push it towards better thinking.
Mm-hmm.
But the paper also flags a potential issue here, this difficulty bias. What's going on there?
Yeah, this was a really interesting finding. They noticed that during this RL training, the model naturally gets better at the easier questions faster.
Makes sense.
But because it's succeeding more often on those, the easy examples start to dominate the training signals. They can kind of drown out the harder, more complex problems where the model still struggles. There's a figure in the paper showing how the mix of easy, medium, and hard samples changes over time.
So the model ends up spending too much effort perfecting what it already finds easy, and not enough time wrestling with the genuinely tough stuff, like a student just drilling easy problems.
Exactly that. Because GRPO compares answers for the same question against each other, it doesn't automatically know how hard that question was in the first place. So a small improvement on an easy question might give the same training signal as a small improvement on a really difficult one.
Right. That seems like it could hold it back. How did they fix that? They mention difficulty-aware weight adjustment strategy.
This is another smart tweak. They introduced a difficulty coefficient. It's basically a score for how hard each training example is.
How do they measure that?
It's linked to how well the model typically does on that example. If the average accuracy, the IOU, is low, that means the model finds it hard, so it gets a higher difficulty coefficient.
Okay, so the tougher problems get more weight in the training updates.
That's the core idea. When they adjust the model during GRPO, the updates coming from harder examples get scaled up. It forces the model to pay more attention to the stuff it's bad at, gives it a bigger nudge to improve on those challenging cases.
Right.
They even tested a few different math functions for calculating this weight and found one, an exponential function, that worked best.
That sounds like a solid way to keep the model learning across the board, not just on the low-hanging fruit.
Yeah.
So with all these pieces, the COTI data, the 2 stages, GRPO, the difficulty adjustment, how did UniVG-R1 actually perform?
The results are pretty impressive, actually.
Huh.
On their main test bed, MIGBench, which has a really diverse set of multi-image grounding tasks, UniVG-R1 set a new state-of-the-art.
Oh, really?
Yeah, it beat the previous best method by a solid 9.1%. That's a pretty significant jump in this field.
A 9.1% improvement is definitely worth noticing. What kind of tasks does that benchmark cover? You said diverse.
Oh yeah, it's comprehensive. Things like spotting static differences, finding common objects across views, object tracking, understanding spatial stuff in multi-view setups, group grounding, region identification, standard referential grounding,
Okay.
plus tasks specifically needing reasoning, and even finding correspondences between images. It's a really tough test.
And it wasn't just good on that specific benchmark, was it? The paper mentioned performance on tasks it hadn't explicitly trained for the zero-shot stuff.
Exactly. Zero shot is crucial, right? It shows how well the model generalizes. And UniVG-R1 did really well there, too. An average improvement of 23.4% across 4 other challenging benchmarks.
23.4% average. That's huge.
It really is. And these other benchmarks included both single image and even video reasoning grounding tasks, so it shows the approach is flexible.
That points to some seriously strong underlying reasoning ability.
Mm.
What about more traditional tasks, like the RefCoCo datasets? Did they test that?
They did. RefCoCo plus appraisal cog.
Mm.
These are standards for just finding an object based on a text description in one image.
Ah.
And UniVG-R1 got the best average performance there, too, hitting 88.20%. Interestingly, it did particularly well on RefCoCog, which is known for having more complex sort of conversational descriptions.
Which again suggests it's good at handling that nuance.
Exactly. It reinforces the idea that the reasoning training helps even with slightly more complex single-image descriptions.
So, top performance on the new complex stuff and on the established benchmarks. That's strong. What about the ablation studies? What do they tell us about why it works so well?
The ablations are always revealing. They basically take the model apart piece by piece to see what matters.
Right.
Key things. Just using RL from the start without that initial CUTI training, much less effective, really shows the value of guiding the reasoning first.
Okay.
Also, more caught data in that first stage led to better results, as you might expect. And the CUTI training was definitely better than just training on coordinates alone, especially for tasks needing reasoning.
Makes sense.
They also confirmed that the GRPO stage provided a clear boost over just doing the CUTI training, and importantly, that difficulty-aware weighting. It consistently added extra performance on top.
So each innovation really pulled its weight.
Pretty much. Oh, and they also showed GRTO significantly helped a smaller 2 billion parameter version of the model, too. So the technique seems broadly applicable.
That's great validation. It sounds like the whole package really works together. Now, the paper hints at examples. Can we maybe visualize how UniVG-R1 might handle a complex instruction?
Sure. Let's try one based on the paper's ideas. One's a close-up of a zebra eating grass. The other is a wider shot, maybe more zebras, also in a grassy area.
Okay.
A complex instruction might be, find the striped animal in the close-up image that's eating the same thing as the other striped animals in the wider shot.
Okay. Lot going on there.
Right. UniVG-R1, because it's trained on reasoning across images, could potentially figure out, okay, animals eating grass in image 2. Find the animal eating grass in image 1. It's connecting the action and the object type across the two different views.
That requires way more than just matching the word zebra.
Absolutely. Or another one, maybe using that workshop example idea. Image 1, messy workshop. Image 2, kid with paint on their hands. The question. Locate the tool in the workshop that could fix the result of the activity shown by the child. The model's internal thought process might be something like, okay, paint on hands, suggest painting, maybe making a mess. Need a tool in the workshop related to painting or cleaning up paint. It might then identify, say, a paintbrush or maybe cleaning rags. Even though the hands aren't in the workshop image, it's reasoning about cause, effect, and tool function.
Those examples really bring it home. Okay, so wrapping this up, what are the main takeaways from this deep dive into UniVG-R1?
I think the biggest thing is that UniVG-R1 really pushes the boundary for universal visual grounding. That combo of high-quality reasoning data, the COT stuff, and that clever two-stage training with difficult-to-aware RL, it lets the model handle complex implicit instructions across images much better than before.
And the real aha moment for me is seeing just how crucial it is to explicitly teach these models how to reason visually. Just showing them examples isn't enough for these tricky, real-world kinds of understanding. You have to guide the thinking process itself.
Precisely. It's not just pattern matching anymore. And it makes you wonder, right? Where could this improved visual reasoning take us? Think about robotics giving robots commands that are less explicit, more intuitive.
Yeah, or augmented reality. Imagine AR systems that understand the scene and your intent much more deeply.
Or even information retrieval, asking things like, find me pictures that have the same mood as this music. As these models get even better at reasoning, what new applications become possible? That's definitely something to think about.